Really pleased to be invited to this symposium. This has been a lot of fun to listen to different kind of talks than I typically listen to, and I think there's been a lot of different things I can touch on, from all the way back from, of course, Dr. Weiss's great keynote talk to some of these more recent talks as well. So let's get to it. So as you mentioned, gravitational waves are this new area of astronomy that we're interested in looking at, and it's been an effort for really decades, including, most importantly, the contributions from Ray and Kip and others that were mentioned in the earlier talk, that eventually led to this new field of astronomy, nearly four decades of work. But people also started thinking about, all right, where else could you do this? How else could you do gravitational waves? So I'm going to talk about the LISA mission. And as you alluded to, it's a really big mission that really is expanding on this idea of these ground-based detectors like LIGO and Virgo and CAGRA. And it happens that this is a design, but it happens that LISA would be sized to fit exactly inside, the sun would fit exactly inside the constellation. That's not where we would put the constellation, but the size is just that. So again, thinking back to one of the earlier talks from some of the biomedical research about the vast difference in scales that people deal with. We also have to deal with vast differences in scales, because we're talking about, of course, universe scales for our sources. We're talking about gigameters, billions of meters for our detector, and then picometers for the kind of measurements we're making with our interferometers. Okay, so a quick outline of the talk. I'm going to talk just a little bit about why we should do LISA. And I think a lot of that's been motivated by some of the science we just heard about, and there's some slight differences, and I'll explain those. And then talk a bit about how the mission works and what the key technologies are, but focus most of it on the interferometry side of that, because that's sort of the theme of this conference. And then, since it is a mission for the future, I'll talk about what the future missions is where we're heading, but also what we've done so far, including a couple of flight demos in space of some relevant technologies. Okay, so why do you want to go to space? Well, the short answer why you want to put a gravitational wave detector in space is the same reason you want to put any other kind of detector or telescope in space. And we just heard about the great lengths and the great challenges that the ground-based detectors have for dealing with the noisy environment of the Earth, including human-made noise, also just natural noise. The Earth is a dynamic place, which makes it interesting to live. It makes it not so interesting it makes it difficult to do very sensitive measurement. If we go to space, we can get away from that. The other thing that was pointed out is that this vacuum system that the ground-based detectors have to build is very difficult to build. It's expensive to build, especially if you're going to start expanding the size of your detector, like the 40-kilometer detector concept that Ray talked about at the end of his talk. It's the single most expensive part of the instrument is the vacuum. Now, one place you can get a whole lot of vacuum is space, right? So if you can get up into space, you can basically make your detector as large as you like. And if anybody is familiar with sort of antenna theory from electromagnetic, E&M radiation theory, basically you want your antenna to be about the same size as the radiation you're looking for, have the same wavelength as the radiation you're looking for. So we can make our detector really big, which helps it couple to longer wavelength or lower frequency gravitational waves. Now, the difficulty with space is it's a pretty harsh environment, right? It's you have to survive launch, which is one kind of harsh environment. Then you have to survive being in space with radiation and big temperature differences and vacuum, et cetera. Maintenance, of course, is hard or basically impossible. And you have to prove all of your technology ahead of time, right? So you can't do the same type of operations that LIGO does, where they operate for a while, then they upgrade, then they operate, then they upgrade. That doesn't work, or at least not without incredible expense involving astronauts. So again, this is getting back to the motivation of why we would do this. There was a version of this chart shown in the keynote talk earlier this morning, but this is the gravitational wave spectrum, and it's meant here to kind of evoke the electromagnetic spectrum. So people are familiar with the EM spectrum, ranging from radio waves up through microwaves, visible light, et cetera, X-rays, gamma rays. There's a similar kind of spectrum with gravitational waves. And so that's what's sort of plotted here with this gray bar here. I didn't know what to use for color, but there's sort of this gray bar where you have the wave frequency spanning several decades or the wave period spanning several decades as well. Now on the top are some regions with these purple bars where we would expect to see different kinds of gravitational wave sources. So from different astrophysical or cosmological sources. And you can see they kind of occupy different regions of the spectrum. On the bottom are a couple different concepts for how people would go about detecting gravitational waves. And just like we need different kinds of detectors to get different kinds of light, we need different kinds of detectors to do different kinds of gravitational waves. So we've heard in the first two talks, gravitational wave talks for this symposium about these terrestrial interferometers. And I'm going to talk about these space interferometers. There's also things called pulsar timing arrays, and then cosmic microwave background polarization that could look at even lower frequency sources. So a couple highlights for LISA for these space-based detectors. So these are million-kilometer scale detectors. So we're looking at million-kilometer scale waves or millihertz frequencies. One thing you can do is, it turns out general relativity is kind of a scale invariant theory, which means that you can do all the calculations in a sort of scale-free way, and then you can just scale the results at the end. So you can take the types of black holes that LIGO would see, and if you crank up their mass by a factor of 100,000 or a million, then their frequencies reside in this LISA band, in this millihertz band, instead of in this 100 hertz or up to even kind of kilohertz band you might get in LIGO. The actual amplitude of the waves goes up similarly well, which means we can see them to extremely long distances. Basically, we can see them farther away than we know any stars or galaxies exist. Now, we don't know whether they're black holes that big, that far away in the universe, that early in the universe, but if they're there, we can see them with something like LISA. We do know that there are black holes that massive in the centers of most galaxies, and we know that galaxies form through a hierarchical assembly of smaller galaxies. So we could use this as a tool to try to probe how galaxies built up over cosmic time. There's a little bit closer to home, but still in the not immediately nearby. We have these things called extreme mass ratio inspirals. So this is what happens when you have a black hole that's a remnant from a star, a heavy star, falling into one of these massive black holes at the center of a galaxy. And it basically whips around in this crazy orbit, and it's probably the most extreme gravitational laboratory that one could cook up. And so that's an important source as well. And then our most numerous sources is one all the way on the right here, is these what we call galactic compact binaries. Now, while black holes and neutron stars get the most attention, they're actually fairly rare objects. Most stars are, including stars like our own sun, aren't massive enough to produce that at the end of their lifetime. Instead, they produce an object called a white dwarf. Many stars are in binaries. Many of these white dwarfs end up in binaries. And for certain categories of those binaries can produce gravitational waves in the millihertz as well. They're much fainter, so we can only see them in our own galaxy, but we can see tens of thousands of these sources simultaneously and actually do stuff like map the galaxy and also do a census of these compact objects in our Milky Way. Okay, I'm going to move down a little bit to the instrument and talk about the sort of fundamentals of why we build the instrument the way we build it. Now, we've seen this chart a couple different times, so I'll introduce it relatively quickly. But I'm going to plot on the vertical axis the strain sensitivity, basically how sensitive or how big the waves are, and on the horizontal axis, the frequency of those waves. And we tend to get a curve that looks like this. And this is what we do if we express our instrument noise as equivalent gravitational wave sensitivity. So basically, any source above this curve we can see, and sources below this curve we can't see. And you see it has a sort of characteristic bucket shape, and it's produced by three main things. The first main thing is the length of the arms. So that scales both the how low or high the bucket is, because the more space we put between our portions of our detector, the more stretching we get, because it's a gravitational wave strain is the change in length over length. So we want to make length big if we want to get a big signal. It also sets the sort of frequency at which we get the most sensitivity. This is this coupling to the wave by having the detector be the same size as your wavelength. So it sets a sort of left and right point as well. At the lower frequencies, the thing we care about most is how stable we can place our test masses. What else is pushing them around? We talked about the vibration from the logging and all that kind of stuff that you need to deal with terrestrially. Even in space, there'll be something that's going to be pushing you around. That sets the low frequency. And at the high frequency, it's how well we can measure the distance between the things. So this is really where the interferometry comes to play in both LIGO and LISA. So what is LISA? So it's a concept for a million-kilometer scale observatory. It actually doesn't go right around the sun. It orbits the sun the same way Earth does. and it follows behind the Earth by about 20 degrees in orbital phase. So that means it's about 50 million kilometers away. And it's this triangular constellation of 3 spacecraft that is connected by laser links. And the point is we want to make this interferometric measurement at the sort of picometer level over these picometer arms to see these gravitational waves. It's a mission of the European Space Agency with NASA, where I work as a significant junior partner. So first, I'm going to talk a little bit about the acceleration noise, because this is kind of neat and relevant to a experiment that we worked on with Europeans a couple of years ago called LISA Pathfinder. So the idea here is that, in principle, if you could put something in space, it's just freely floating. It's not being affected by any other forces. But when you start to look at it at the level of picometers and such, you worry about things like the solar radiation pressure, micrometeorites, and all these other bits that can be pushing around your spacecraft. And the idea people had was, well, what if you put a test mass, a little mass, inside your spacecraft, and you don't touch it? You have a hollow cavity. Now here I'm showing it as if like the whole spacecraft was hollow, and in reality it's just a few millimeter gap. And what you do is you use some sensors to measure the position of your spacecraft relative to your test mass. So then if you have a force, like let's say the solar radiation pressure pushing down on the top deck of the spacecraft here, it pushes the spacecraft, but not the test mass, because the test mass is inside, it's sort of shielded. Now, eventually, the spacecraft is going to run into the test mass, which would cause a problem. So what you do is you use your control system to fire some thrusters to balance that force, but you're still never touching the test mass. And if you do this properly, you basically can act like a flying shield that's protecting your test mass. Now, to demonstrate that, the Europeans led a mission, again, with NASA contribution called LISA Pathfinder. And we use, here's a picture of the gold platinum test mass. It's a few centimeters on the side, weighs a few kilograms. It's inside this electrode housing, so we can sense the position of it. We also use a laser to sense the position along one axis. And then we use these micro thrusters, which have a force that's about equivalent to the weight of a mosquito to push around our spacecraft. And what we'd like to say is that the LISA Pathfinder spacecraft gave us all of the noise, or at least most of the noise, and none of the signal, which is, if you're interested in understanding the instrument, it's exactly what you want. Here are the results of LISA Pathfinder. So there's a nice photo of the launch from Kourou in French Guiana. And here are a spectrum of its performance of this acceleration noise, with the performance here saying what we wanted to achieve. What we actually achieved in the end was this red curve many decades below, and this line here is what we needed for LISA. And so we can show that we basically demonstrated what we need to do for LISA on the acceleration noise side. Also, Pathfinder included an interferometer, which I'm highlighting because, number one, it was relevant to the symposium, and number two, we just published a paper recently on it. Now, most of what we saw was sort of actual motion of the spacecraft. So this is position noise versus frequency in the LISA band. This goes down to, here's a picometer here, if you can't quite read this. Here's a femtometer down at the bottom. And this is with a simple Michelson interferometer, so none of the fancy cavities or anything that LIGO uses, and only a few milliwatts of light. And it shows you sort of how stable, what the benefits of having this extremely stable space environment. It's also at very low frequencies, which are notoriously difficult to control things like temperature and that type of stuff. So to scale up to LISA, we need to do this over a long distance. And so we can't do the same techniques that LIGO uses, where we recycle the light back and forth, because the light basically spreads out, and we launch something like 1 watt or 2 watts of light from our spacecraft. We only collect a few hundred picowatts just because of the spreading of the light, which is still plenty of photons to figure out the position to a picometer, but you can't reflect it backwards. It's just not going to work. So instead, we work much more like a radio transponder, where we send light in each direction bidirectionally, and we basically measure the phase of the light we're transmitting relative to the phase of the light that we're receiving, and we just record that and stream it down to the ground. And by measuring that at several points along the constellation, we can actually reconstruct the position of the constellation and the geometry of the constellation, and see the distortions that are caused by the gravitational waves. There's also been a technology demonstrator for this, as long as also for other things. There's a really interesting satellite called GRACE, or GRACE Follow-On, which is a NASA-German collaboration to do geodesy. So here you see a map of the gravitational potential of the Earth at very high resolution. So you can see mountain ranges, and you can see, if you look at it seasonally, you can see all kinds of some of these events like flooding and glaciation and all kinds of stuff. And the way it works is basically there's two satellites that are orbiting the sun in a low Earth orbit. They track the range between the satellites, and they see some acceleration anomalies that come from the gravitational pull of basically the mass concentrations underneath the spacecraft. In this recent thing that's called GRACE Follow-On, which is a data continuation mission, a second version of it, they included a laser demo to basically measure the laser range between these two satellites in parallel with the microwave range, which is the standard instrument. And so this is at a 220 kilometer separation. And here's some data from GRACE, again, published relatively recently. You can see most of this big wiggles is actually the spectrum of the gravitational potential of Earth. But as you move down to higher and higher frequencies, eventually you hit the interferometer noise floor, which is sort of sub-nanometer noise floor. Now this is with a single arm, but over 200 kilometers, which is kind of neat. So this is partly demonstrating what we would want to do for LISA. And a lot of the sort of basic techniques, including things like how do you do acquisition and tracking, are very relevant for LISA. Now what's left to do? So the main thing they're left to do is to develop some of the remaining technologies. There's a few that weren't developed on either Pathfinder or GRACE Follow-On. That includes ultra-table telescopes. So we actually use a telescope not to make imaging, but basically to compress the beam that we're transmitting and then to collect some of the beam. So basically to mitigate this huge amount of diffraction that we get when we transmit from one side of the constellation to the other. That's something that's being worked on at NASA Goddard, where I work. We also need to take our laser power, and we don't need to have the same kind of laser power that they have in LIGO, where you have kilowatts of laser power, but we do need a few watts, and it needs to be stable, over our measurement band. So it has to be very stable in frequency and intensity, which is challenging, and even more challenging, it has to last for the lifetime of the mission, which could be up to 10 years of science orbit, maybe up to 15 years in orbit. And lasers are kind of finicky things. Space is not a great environment for lasers. So getting them to operate for that long, and you also need a constellation. You need 6 of them to be operating by the end of the mission. So that's a big challenge as well. So here's a picture here of a laser that's also being developed at Goddard. There's a couple other bits and pieces that are being developed, including an optical bench. There's just a schematic here. And a charge management unit. We actually use ultraviolet light to control the charge on these test masses. Otherwise, it builds up from cosmic rays. The other main thing I would say, and this is almost more important than developing new technology, we have to move from these technology demonstrators like LISA Pathfinder and the LRI on GRACE Follow-On to an observatory. And that means you can't just make one of them, you need to make 6 of them or 10 of them. And you can't have it just last for the short mission you need to characterize the performance. Pathfinder was an 18-month long operation. We need to, as I said, to last for sort of 15 years. And so there's a lot more of the engineering that goes into making an observatory as opposed to making a technology demonstrator. And that's a big focus of our efforts right now. So where are we? So the mission is on track for science in the 2030s. It's in what European Space Agency calls Phase A, which is part of the design stage. We're near the end of Phase A. There's a number of industrial contractors and universities and all kinds of people working to do detailed designs of the spacecraft. There's an important milestone called mission adoption, which is coming up in a couple of years here, and that's where we have the final design. It's costed. There's a schedule. We know what the partnerships are between, say, NASA and ESA and its other European partners. Launch would be in the 2030s. It would take about 2 years to get into that operational orbit and commission the instrument and start science. We would do at least 4 years of baseline science, but we carry enough fuel and other supplies to do 10 years of science in total. And so that's the summary of the talk there. And as I said, it'll be the largest instrument ever constructed. So you have to be careful with all these qualifiers, but I would call it the largest sort of purposeful instrument ever constructed. And the interferometry it's relatively simple compared to the ground-based detector. So when I go to conferences of gravitational wave people, the interferometrists that work on LIGO and Virgo are not so impressed by LISA because it's kind of boring. But its science potential there is quite amazing. The technologies are really well in hand through a lot of this development that's gone on through the decades, and especially these flight demonstrations. And the detailed mission design is well underway, and I think we're on track for launch in the 2030s. So with that, I'll be happy to take any questions that anybody may have.